But hopefully what you saw with these problems is that you can actually differentiate between different functional groups using the mass, or using the IR spectra. And anything you can do to narrow down possible compounds, and it's probably 13 million organic, it goes from 9 to 11. I'll guesstimate that it's probably 13 million organic molecules. If you can narrow that down to, I don't know, a million, that's pretty good. If you can, at least by functional groups, you can do that with some of these. Now, these are fairly simple molecules that have maybe 1 or 2 functional groups in them. It gets a little more complicated when there's more than 2. Okay, so the next technique that we're going to talk about is mass spectrometry. Now, spectrometry doesn't involve any kind of light absorption, so that's why it's spectrometry versus spectrophotometry or spectroscopy. Spectroscopy means we're using a light, we're using electromagnetic radiation. We are not spectrometry. So the mass spectrometry people get upset if you call it spectroscopy, which I will probably, the over-under on that's probably about 4 in the next few minutes. So here's what we do in mass spectrometry. It's going to give us the molecular weight of the molecule, and it's going to break the molecule up into pieces so that if we had all these pieces, we're like putting the puzzle back together. And so in mass spectrometry, what I do is first of all, I've got to get my molecule into the gas phase. And the simplest way to do that is simply to heat it so that the molecule goes into the gas phase. Now, it can't decompose. It's somehow got to get into the gas phase intact. And then once it's in the gas phase, then I have to break it apart into what's called a radical cation. So it's going to have both pieces. And the easiest way to do that is to basically pass the molecule through an electron beam. So I have this beam of electrons, and that beam of electrons is going to smash into the molecule, and it's going to kick out an electron from somewhere in the molecule. When you lose an electron, most molecules have an even number of electrons, so they end up with an unpaired electron, and because they lost an electron with a negative charge, they end up with a positive charge. So that's why this is called the radical cation. And then that radical cation can be analyzed, or it just simply starts breaking apart into pieces. So that's the basics of how we're going to do mass spectrometry. It's a little more complicated than that. So we place a sample in, get it into its gaseous form by heating it. The gaseous sample is bombarded by an electron beam to form the radical cation. And then we have to measure the mass of the radical cation and all of the pieces that it falls apart into. Okay? So in the instrument, this is a classical instrument that probably nobody uses anymore. Matter of fact, I don't know that I've seen one of these in a long time. We have to remember some basic physics here. So once you take the molecule and you get it and you smash it with the electron beam, then you have to get it into this tube. Now, all of this is under vacuum, because if you just have gas molecules in there, atmospheric gas molecules, those things are going to be bouncing into them. They're going to be reacting. So we have to do it in a molecule-less environment, meaning we have to do it in a high vacuum. So we have to keep everything out of here. Reality, we don't keep everything out. There's probably a few water molecules, a few CO2, a few oxygens, and nitrogens, but we got to get rid of most of it. So this is all under vacuum. You can move ions around pretty easily. You want them to go into the tube. You put like a positive charge on this. Those negative charge on this, the positively charged species will go right to it. put a little pinhole. Everything that smashes on the outside doesn't make it in. Everything that makes it in comes in a straight line. So then the ions come in, and then they go into a magnetic field. Anything with a moving charge has a magnetic field. And more importantly, anything with a charge that's moving can be deflected by a magnetic field. And so we build in this like right angle tube so that depending on the magnetic field we have, we can bend the molecules that have exactly the right mass to charge ratio, because they'll have a certain magnetic field. If they match, we can get it to bend around this tube and then come down and be detected. Anything that's too heavy smashes into the side. Anything that's too light is deflected too much and smashes into the side. So if I know all the equations about how much, and if this is an electromagnet, how much current to apply to that magnet, and I've sort of calibrated it so I know, oh, a mass to charge ratio of this will turn, and then if I change it a little bit, oh, now this mass will turn, then I can calibrate that so I can scan through all the masses and measure the number of ions that make it to the detector. And so this is my spectrum. It's a right side up spectrum where this is the number of ions and this is their mass to charge ratio. Now, mass to charge ratio, what does that mean? For normal molecules that we're going to use in this class, the charge is 1. So if the charge is 1, that means the mass is the molecular mass of the molecule. Biomolecular mass spec becomes much more difficult because sometimes you can get charges of +2 or +3, and we're measuring the ratio. So for us, it's going to be really, really simple. The heaviest molecule that makes it through is the peak that's the farthest to the right. That's called the molecular ion, which I'll show you in a minute. That's the molecular mass of the molecule, the peak farthest to the right. When it starts to break apart, it starts to form fragment ions, which weigh less. And so at best, well, at worst, you're going to get the molecular weight of the molecule. At best, you're going to get all the pieces that you can put back together to determine the structure. And this, and if you apply this in a little more complicated fashion, you can determine amino acid sequences or protein sequences, which they do like in places like the clinic all the time. They have a division that does nothing but mass spec. I think one of their papers on how you're not supposed to eat that much red meat, and they now have a lot of evidence for that. They did that all by mass spec. It's on the cover of the NIH, the National Institutes of Health page. I looked at to see, we've had many John Carroll students do internships or be employed in the mass spec facility, so I just looked to see if there were any John Carroll students. None that I could identify, but they've done a lot of mass spec down there. So that's the technique. And so we have to make these charged molecules. If it's not charged, it just smashes into something and it never makes it to the detector. Okay. So the way we get molecules into the gas phase here in our mass spec is to use a GC mass spec. So I mean, if you've ever watched like anything with any crime show, any of the CSIs, any of the NCISs, I think in the NCIS it has a title of major mass spec, which I don't know how it got that, but it solves every crime. It's like DNA. If you have a GC mass spec and DNA, you solve every crime on the face of the earth. And it's not that easy. But what we do is we combine a GC where I inject my sample, and you know from last semester, the samples separate out. Well, every compound that comes out goes into a mass spectrum, and you get a mass spectrum of every peak that comes out of the GC. Not these GCs over here, because we got big, really broad peaks, but the one next door that gives you very narrow peaks, so that in theory, I can identify every molecule that gives me a peak in the GC, because I'll get its mass spectrum. So that's what we have next door. Ours looks like this if you've ever been in there to see it. It has an auto sampler, or you can inject by hand. And basically, I take a syringe full of material, I inject it here. It goes through the column. It goes through this really hair-thin column and then goes into the mass spectrometer, which is over here. And it's all under vacuum, so it's all in case there's nothing interesting to see. Except ours works a little differently. There's no right-hand tube. Ours is called an ion trap, so it takes the ions and it like figure eights them around and then kicks them out one at a time in like less than hundredths of a second. So that's how it counts ions. So that's one of the powerful methods is now I can look at the identify, bless you, of every molecule in my mixture. So when you run a GC mass spec on anything, you'll get a gas chromatograph part, and then you'll get a mass spectrum of each of those peaks. So we can analyze our product. We could analyze our products on using this instrument. If we had, it'd be better if we had like 100 sample carousel. We only have 10 at a time. And also if our compounds were super clean, because otherwise it gets gunked up and that stuff shows up in everybody's sample. But here's the GC of, this is what? This is lavandin. Lavandin is an essential oil. It's not lavender, sort of like lavender, but not quite lavender. It's lavandin. Last semester we did the steam distillation to make clove oil, right? So we could have injected our clove oil, and I guarantee you we would have seen more than 2 peaks, because this instrument's far more sensitive. So I can take this peak, for instance, and when I click on it, here's its GC mass spec. Here's its mass spec. So when I look at this, I see the peak farthest to the right is 154. So that means that's its molecular weight, is 154 AMUs. And so that's pretty good. And then each one of these is a fragment. And we're going to talk in detail about fragmentation next week, primarily because the fragmentation involves carbocations and their resonance structures. And so this is a way for me to sneak all that information in that we'll use in lecture about the stability of carbocations and resonance structures when we have allylic carbocations and things like that. That's what we're going to look at next week for each of the functional groups. And that's one of my learning outcomes is that we get more experience with determining structures. Right now, if you talk about carbocations, tertiary, okay, right, stable. Secondary, primaries, we say never form. Yeah, in mass spec, we're going to see primary carbocations. So this is going to be the exception to the rule. Why? In solution, primary carbocations aren't stable enough to form because there's not a lot of energy. In the gas phase, in a heated environment, they can form. So they're only forbidden in the lecture class, not in the lab class. So we'll actually see primary carbocations. But that'll be next week. So that's the kind of information here I can get. But starting with, okay, the peak farthest to the right is 154. That's the molecular weight of this molecule. What else can I get? Okay. Well, that lets me determine the molecular weight of the molecule from a very small sample. When we look at, well, what have we looked at recently? Recently, I had a high school student come in because she had 4 essential oils, and she wanted to determine which one had compounds in them that would be antibacterial or antimicrobial. She didn't know what a mole was because she hasn't taken high school chemistry yet. So I think she's like in 9th grade. pretty ambitious project. I mean, the senior instrumental students were doing the same project, but when the high school students come in, they come in to use our instruments. So a lot of times they're doing the same projects as the seniors. But so that was kind of tough because I had to explain without her knowing any chemistry. And that's my usual question. Do you know what a mole is? And if it's a furry thing, they haven't taken chemistry. So what she had to do was have her 4 essential oils. And then she had to take out 10 microliters of each oil, and put it into 1 milliliter of dichloromethane. And then dilute that sample 3 more times, each time 100 microliters to 1,000 microliters. So she ended up diluting that sample to 1,000. And so in her final sample, she had, instead of 10 milligrams, she had 10 nanograms, or 10 micrograms. Anyway, she had that. This is always what drives me up the wall when I have to go from milli to micro to nano. So anyway, that's what she had. She had a very, very good dilute solution. But there's more than enough in there to detect. So we would run them and determine the GCs, and then we had the fun of having to go through and figure out what each and every peak meant. What was the identity of each and every peak? So I'll talk about that in a moment. So we were getting the molecular weights for each one of those. My story there was how small the sample can be. If you have a drug test for whatever, they're going to do mass spec, either on, I suppose, your urine, your hair, whatever. And they're looking for metabolites of illicit substances or whatever substances they're looking for. And so that's a very tiny amount. There, what they're doing is they're looking at, okay, I don't know, take your illegal drug of choice. Not literally take it, but use it as an example. Like, they might be looking for cannabis, right? That's the big one now. And I think Hawking College now has the contract to test all of the cannabis in the state of Ohio. I don't know why we didn't go for that contract. Well, probably the cross has something to do with it right at the moment, since it's still illegal according to federal law. But anyway, you're looking for a particular metabolite of somebody that's maybe had some marijuana or a whatever it is, THC. So that's what they're looking for. In a GC, that means that peak shows up at exactly this time, and it has exactly that mass spectrum. And so if that's the case, that's a positive hit, maybe, for that metabolite. If it doesn't have that retention time, it's not that compound. If it has that retention time but not that mass spec, it's not that compound. And so that's the small amount of material that you need to do the mass spec. We're determining molecular weights. We haven't calculated degrees of unsaturation yet, but I'll show you that if I have the molecular weight, there's only a certain set of formulas that fit that molecular weight. So I've narrowed down my compound search to maybe 20. And I'll show you that in a moment. And then the fragments can help me put the structure of the molecule back together. And we'll talk about that next week. So what about the molecular weight? Well, here's methane. So if I took methane and I did a mass spec on it, I would see a peak of 15, or I would see a peak of 60. That would be the peak farthest to the right, because carbon is 12, hydrogen is 4, total of 16. Now, that would be the molecular weight. That's what's called the M dot plus, the molecular ion, is the biggest mass in the spectrum, is the molecular ion. So this molecular ion then will begin to break down. And the way it breaks down is, how about that CH4 dot plus loses a hydrogen atom? Well, if it loses a hydrogen atom, that leaves it as a CH3 plus. If primary carbocations are bad, CH3 pluses are even worse. But yet I still wrote it. Oh, and it's there. So this mass spec is a totally different ballgame. High energy species can exist. So then there's a fragment. So it lost an H dot. Then if the CH3 plus loses an H dot, now it's down to a CH2 dot plus. And so now I see that peak. Of course, every fragmentation gets smaller and smaller. So it's those fragments that help us put this molecule back together if we know how it fragments. There's a problem here. So there's a little teeny tiny peak at 17. Wait, methane weighs 60. So how am I getting a peak at 17? Well, let me skip ahead here to table 13, or page 13, I think. Or not page 13, it's whatever the spectrum is. It'd be nice if all of these atoms weigh the same, but remember we have isotopes. The mass of 12, carbon's atomic weight isn't 12, it's like 12.11, because we have to take a weighted average of all of the isotopes. So there is a carbon 12, which is 98.9%. There is a carbon 13, that's 1.1%. And there is a carbon 14, which is a trace amount. That's the radioactive one that's used for like carbon dating and archaeology. So only 98.9% of the carbons are carbon 12. 1.1% are carbon 13s. So if we go back to that, spectrum, what's the peak at 17? It is out of 100 molecules, it is the one that has a mass of 13. It's the carbon with a mass of 13. So if this is a carbon 13, 13 plus 4 is now 17. And in theory, I don't think this is drawn to scale, although it might be. This peak should be 1% of that peak, given that it's a probability of 1% carbon 13 for every 100 of carbon 12. So that's what's called the M plus 1 peak, because it's now got an additional AMU on it. And that peak actually can be useful, because if you think about it this way, for every carbon that's in the molecule, there's a 1.1% that carbon is carbon 13. So if you took the ratio of this peak to this peak and divided by 1.1, it would give you a rough approximation of the number of carbons in the molecule. You're not impressed. You'll see the wow in a minute. So in other words, I can determine the number of carbons in my molecule. And that's going to help me a lot. Maybe. So that's what's called the M plus 1 peak. So that's where we get the atomic, molecular weight from. So if we looked, for instance, skipping 2 slides ahead, if we look at nonane and we look at pentane, again, we see lots of fragments. The peak at the end of 128.86, that's the molecular weight of the 3-methylpentane and the nonane, 128 versus 86. And what we'll see next week is that as the molecule begins to fragment, we lose groups. And by fragment, what I mean is I'm just going to cleave a carbon-carbon bond. So for instance, if I have 3-methylpentane, the beauty of 3-methylpentane is if I cleave that bond, if I cleave the, I don't know how many people are going to go back and watch this, but if I cleave that bond, what I'm left with is a nice secondary carbocation. And what I've done is I've lost a CH2CH3. How much does a CH2CH3 group weigh? Well, 2 carbons times 12, that's 24 plus how many? 5 hydrogens. So that's, what are they, 24 plus, so 29. So what's 86 minus 29? 57. So this was a loss of 29. For this one, going from 86 to 71, I lost 15. What's 15? Carbon and 3 hydrogens. So you can begin to kind of see, you can work this from both ends. You can say, okay, what in this molecule weighs 57? Or what in this molecule weighs 71? Or you can say, I'm starting with an 86, what can I lose to get to 71? So all of these are pieces of this. And so somebody who's really good at mass spectrometry, which I'm middle of the road for stuff I do, you could use that and determine the structure probably from scratch. So that's what we're going to talk about more next week, about the fragmentation. But just from the molecular ion, just from the molecular weight, what could I get? Well, there are books of molecular ion masses. And this one's from the spectroscopy book I had as an undergraduate in circa 1984. So, of course, it had the printout from the dot matrix printer. And these are all of the different formulas that weigh up to roughly 154, rounded up or down. That's useful. I took my 13 million organic molecules, and I've now narrowed it down to that many. Now, remember what I said about the M plus 1p? That if you use that formula, you could see how many carbons were in there. I can narrow this list down even more. That's the ooh and the ah of that, is the fact that I went from 13 million to this. Now I'm going to go from this to an even smaller number. And we don't do that a lot, but we can. I mean, we can do that. And so that's what's really useful. Now, there is something called exact mass spectrometry, which our mass spectrum will only determine the masses to whole digits. But if you have a really sensitive one, you could get like 4 decimal places afterwards. So if you take into account all the isotopes of all the atoms in your formula, those 154s, they all have different 4-place numbers after them. And so if you had an exact mass spectrometer, you could actually narrow this whole list down to 1 or 2 by comparing the mass to 4 decimal points. I think Case has one of these. If you make a new compound and you're going to report it, they now require, I think, that you have an exact mass to back up your structure. And that's tough because you got to get the thing super pure, because any impurity will throw all of this off. So, well, it might not throw this off as much as it used to throw off determining the percentage of carbon and hydrogen in the molecule. So I can determine the structure from mass spec. I can at least narrow things down. And I've only kind of used the narrowing down of the molecular weight maybe a couple times recently. Well, recently, last 10 years. So not only do people get foreign objects in their bread. There's also, if you put yeast, obviously, in the bread, and you're supposed to bake it to a certain temperature to kill the yeast, and it has to be a certain temperature at a certain time, and then the yeast die. If the ovens don't reach that temperature, the yeast don't die. And so then you have a piece of bread with live yeast in it. Well, those live yeast have to eat. And what they do is they eat the bread. And what they do is they produce then things like ethyl acetate and other volatile compounds, so that when you open the bread up, what did the person who gave it in said, "Hey, it smells like there's fingernail polish in there." Well, from General Chem, if you did fingernail polish has acetone and it's got ethyl acetate, and so it's like, okay, that makes sense. So then I had to put the piece of bread inside of a vial, seal it up, take a sample of the gas inside of there, got the peak, didn't get enough of it to do a search, but I got enough of it to get the molecular weight, had like 5 molecular weights. I'm like, okay, this is ethyl acetate. Then I'm like, well, that makes sense, because she said they were trying to poison her, and she was going to go to the TV and all sorts of stuff. And that got really weird after a while. So if you open up bread and it smells like fingernail polish, get rid of it. Don't eat it. Somebody ate it and they got sick, and then they tried to tell. I said, there's live yeast in it. The guy got my report. He got my name somehow, which I usually never let happen. He's like, "You said that it wasn't going to make me sick." And I said, "No, sir. I am not qualified to dispense medical advice. So I did not do so. Maybe the company told you weren't going to get sick, but that's not me." So my legal team says, all I tell you is what's there. And I always use words like most likely, consistent with. Actually, in court, as a forensic person, you're not allowed to say you have 100%, that anything's 100% authentic. They do not allow that. You have to have a probability for everything. Which is why in forensics, they're starting to throw out evidence like teeth marks and tool marks and stuff, because you can't put a probability on them. So if you take like wrongful convictions, that's the big problem there, is that they're coming in and saying, "Oh, this teeth mark matched exactly." And then somebody's saying, "Well, what about the probabilities?" And then you can't establish probabilities. You can with DNA. You certainly can probably with GC Mass Spec. But so anyway, if you take that class, you'll learn all about that. That's Dr. Dowd and Dr. Shivani's class, I think. So if you've taken it, you've already heard about it. But anyway, so just having the molecular weight helps you out a lot. But actually, this idea of the isotopes, you can do a lot of things with this. We talk about making chloride and bromides, alkyl chloride, alkyl bromides, alkyl iodides in class. How do we know that bromide is a better nucleophile than chloride? If we actually mix something together where we had those two in competition, because the chloride has isotope, it has a 75-25 ratio of the two isotopes, and the bromide has a 50-50. Not only because the molecule would have to add up to that mass with chlorine versus bromine, but you would actually see multiple peaks in your spectrum. So for instance, here's the bromine. So if you had bromobenzene, you actually have two peaks that are 50-50, because one is the bromine 79 and one's bromine 81. And they have near 50-50 isotopic ratios. Whereas if this was a chlorine, it would be, number one, it's at a completely different mass, but number two, it would have a 75-25. So you can actually tell the difference between halogens by using their isotopic ratios. And there's lots of things, there's lots of other things you can do with those isotopic ratios. I only threw in, let's see, I only throw in this spectrum, or this slide, because this shows you all the different patterns that you can have, depending on whether you have 1 chlorine, 2 chlorines, 1 bromine, 2 bromines. Sulfur has different patterns. These are all for the molecular ions. And they're all based on the fact that sulfur has 2 different isotopes of varying percentages. So you can get a lot of information from mass spectrometry, from its molecular weight, and also from isotope ratios. I think Dr. Kwan they were trying to figure out at one point, they made molecules and they were trying to see if it was a bromine or a chlorine or an iodine. And I think when we mass spec'd it, you could see this compound had the chlorine, this compound had the bromine, this compound had the iodine. Because iodine is just one simple P. So you can get some information that way. All right. So one of the best, I'll just show you this example as this is kind of the reality of the mass spectrum. One of the isotopes that shows up a lot that we see, and it's an impurity in the system, is silicon. So silicon has a whole bunch of different isotopes, and they create peaks that sort of have this like skateboard ramp type feature. So in our compound silicon, or in our machine, not our machine, our instrument, there's a lot of silicon. There's a silicon septum where the syringe goes through. There's silicon coating some of the glass surfaces, and so when that breaks down, it shoots through the instrument. And so this is a sample of the vapor above a natural light beer from years ago, from somebody else that was here, Dr. Miller, who was trying to determine like skunkiness, if you could detect the skunkiness of beer, because the skunkiness is a disulfide that comes out. I didn't know anything about skunky beer, but apparently there are people that study this intensely. Scientists, not weekend people that study this intensely. So she was trying to determine that, and for every single one of these peaks, there was this pattern, so I'm like, that's just garbage coming off the column. We can't really determine that. So all those peaks in the GC are just decomposition. We couldn't determine anything that was in the headspace, which is what the vapor above the liquid is called. Where do people use the GC mass spec a lot? Right, this is the last part for today, so everybody can get excited. If we know nothing about chemistry, like my high school student, we could actually go through and we could still determine most likely what her compounds were by using a database. And so if we go back, not to her essential oil, but I had a student, Natalie, who was working on lavender, lavandin, and spiked lavender. Those three, trying to determine like how we could tell the difference between them and what the chemical difference was. And so we had like 50 samples. And first thing you got to know is when you buy something, it's not always what you think it is. So you have to somehow go through here and classify them, find the outliers, throw those out, find the ones that are questionable, throw those out. So you find basically if you buy 2 lavenders from 2 places on Amazon, they're going to be slightly different. Maybe because the lavender came from France versus Spain versus... I know way too much about this stuff that I should. Well, let's go back to lavender. This peak. So what's that peak? What is the identity of that peak? I know it weighs 154. So now what I can do, and what most forensic labs will do, is that they say, hey, that's a fingerprint. The intensity of each one of those peaks can be digitized and make a fingerprint out of it. Not a literal fingerprint, but it's a pattern. So when you buy a GC Mass Spec at $80,000 plus, they will give you one and only one copy of a database that contains probably 200 and some thousand compounds. So what you do is you click on that peak, you come over here and you say, search that spectrum against the 100,000 or 200,000 or 300,000 compounds in the database, and it comes back and it says, you know what? This one is a I don't think that's actually correct. I think it's an 82.3% match. That was 100% pure of that compound. So it comes through and it says, hey, okay, the first thing it says, eucalyptol's an 82% match. And then eucalyptol's in that database like 7 times. So they all show up. And usually when you see them all, when you see the same name show up over and over again, that's a pretty good hit. Now if I wanted to, I'd buy actual eucalyptol and I would inject it into the GC. And if that eucalyptol came out at exactly that same temperature and gave me that exact spectrum, it's a positive hit. So then I can go through and say, okay, that component in the lavandin is eucalyptol. And so I could go through each one of those compounds and at least get an idea of what each one of those compounds is. Which, with these essential oils, the high schools, we end up doing that. Anya was the high school student. Her sister had done a project with me like 6 years ago, which is how the mother knew to contact me, or the science teacher. I got to stop them from doing that too. But we learned stuff in science fair projects. Like we learned that there's differences between those 4 essential oils, or white chocolate doesn't have any caffeine in it. That was another thing we learned years ago. So what we did was we then went through and compared and determined the identities of each one of those compounds, so that her one essential oil contained this one, the other one didn't. Or how much did they contain? One essential oil might contain a lot, another a little. So we can use this. We can use these databases. Dr. Saporito in biology, right? He's got those cute little frogs. Poison frogs, which are sometimes poisonous, sometimes not. And what he does is he studies the alkaloids that the frogs use. And from what I know about the little frogs, they only become poisonous when they eat stuff that makes them poisonous. And so he studies like what are the compounds, what are the alkaloids that are in the insects versus when they go into the frog. And I don't think in that case the frog's okay. I think they just take the stuff off the frog. I guess. I've never heard anything about frogs. There's no bloody frog. It's not like the rats downstairs. Anyway, right? You didn't hear that. But if you're in a neuroscience concentration, you probably know about that. Anyway, frogs are okay. So that's how he can track the alkaloids and where they come from, and which ones are being made, which ones are being transferred by them ingesting it. So he uses the GC Mass Spec a lot. He actually has his own that he got from his PhD advisor that has a GC connected to an IR connected to a Mass Spec. So he's able to get an IR of the compound as it comes out along with the Mass Spec, and he has the database that his postdoc advisor had built up after many, many years. And it was if I look up the reference of this spectrum, there are actually spectrum from his postdoc boss that have been donated in there. So you can identify the types of compounds that are in there if you don't have the authentics. The last story I'll tell is Dr. Wayner brought me a little piece of amber. in a vial and wouldn't tell me what it is. I'm like, it looks like it's amber. And he goes, I said, what is it? I can't tell you. Number one, I should have been really suspicious about that. So he's like, well, can we try and figure out what this is? So we tried NMR, it didn't work. Tried Mass Spec and injected it, and we dissolved it in dichloromethane, injected it, got all these different peaks. Then we went one by one, and once we found out sort of what it was, you can actually click in one of these, and it'll take you to the database, and it'll say this compound was found in this material. And so when you do that for 20 different compounds, you get an idea of what the sample was. And it turned out it was like varnish or some wood covering. And then I'm like, okay, so it looks like it's kind of varnish. Over time that varnish might, the shellac or whatever might just kind of move down the cross, the same way you see as the old, like old windows in New England, the glass kind of. So, well, I didn't tell you before it was a cross. Anyway, so then he says, okay, I said, what is this? It came from the bottom of a cross at a church downtown. And nobody wanted to analyze it, apparently. They thought it might be something miraculous, blood or something like that. And it was just the wood, just the varnish on the wood. But other students have done their projects in instrumental where they've collected stuff from like contaminated fields. So you might be able to say, okay, what's contaminating? Are these all oil components? Or these? So you can get a lot of information from this. What information are we going to get from this? Number one, we can get the molecular weight. That's pretty good. Number two, we're going to look at the fragmentations of each of the molecules next week. And so the idea there is that when you break the dot plus up, you get a plus and a dot for each one. So you break it up and you get dot plus, dot plus. And so it'll break up to form the most stable carbocation. And so we're going to use those fragmentation patterns to review or preview the stability of carbocations and their resonance structures. And so that's what we're going to do next week. There's no homework assignment for the Mass Spec. I will give you one next week, and we'll do some problems in class. Okay, so what's due next week? The homework problems that say, the IR homework problems that say they're due next week. I'll post this lecture because I recorded everything, which I probably shouldn't have, but I did. I'll post this on the lab website, and I'll probably end up posting it on my lecture website to replace the things at the bottom of the page because they're not very good. All right? Okay, so I'll see you next week. Then after next week, we'll be halfway through these. Again, you just have to be patient. We've got to go through this, and then we'll actually start doing lab experiments.